Okay, this paper here is like a Nobel Prize level paper. This is a big deal. This is a major thing I'm talking about. If you want to pay attention to the talk, this is one of my most important talks that you understand this. Okay, the light effect on water viscosity, implication for ATP synthesis. So what this is about is the infrared light that comes from the sun, also comes from incandescent light bulbs. It's interacting with the water around the ATP synthase enzyme that makes ATP inside the mitochondria. And it's changing the water from a gel into a liquid phase, and that's enabling ATP synthase to spin faster. The ATP synthase is like a motor. They call it a nanomotor because it's very small. It can spin 9,000 times in 1 minute. Think how fast that is, 9,000 times in 1 minute. And that's why also all these stupid jerks, these trolls on the internet try to tell me, oh, you don't need to believe in God to understand science, Darwinism. I'm like, get out of here, you idiots. You don't know anything about biochemistry. Real biochemistry, the people who know, they look at stuff like this. This little miniature motor, and you could have 100,000 of them inside, 100,000 mitochondria inside a cell, and the mitochondria itself will have tons of these little ATP motors spinning 9,000 times per minute. It's incredible to make ATP, adenosine triphosphate, which is the energy currency of a cell. It's like a $20 bill in a cell. And so what's happening is there's 4 phases of water. I'll show you a picture in a moment. But the near infrared light comes in here, and when it hits the water around ATP synthase, it liquefies it from gel to liquefaction. And this is one paper, and there's a bunch of other papers that'll tell you the same thing. But this is just one of the landmark papers on the subject, okay? Here, let me show you some more slides to this effect. First of all, we got to talk about the phases of water. Everybody knows 3 phases of water, but there's 4 phases. So there's liquid phase of water, okay? You can drink that, okay? Then there's water vapor. The evaporation of water becomes a gas, or when you heat it, it becomes a gas. The ice or solid phase of water, like an ice cube here. And then here is a gel phase. Like when you crack an egg, you don't get water coming out. Like humans, for example, we're supposed to be 65% water. How come when we get a cut, we don't bleed water? We bleed blood, okay? How come water doesn't come out of us if we're 65% water? How come when you crack an egg, another animal that's mostly water, why is it that you get a gel instead of water? Because the water's in a gel phase. That's the answer. It's a semi-solid phase. Gerald Pollack has written the most about this. This is a very important concept in physiology, okay? Trust me, this is Nobel Prize work. It's big stuff. And it's going to explain a whole bunch of stuff. In a moment, I'm going to go into the consequences of this and how this explains a lot of things inside cells that aren't widely understood. Here's the typical mitochondria. Outer mitochondrial membrane is called outer mitochondrial membrane, OMM. The inner mitochondrial membrane, IMM. And then the space in between the outer and the inner membrane is called the intramembranous space. That's where the protons get pumped, okay? And then the yellow stuff here is the mitochondrial matrix in the center. And this is in a gel phase, the mitochondrial matrix. You need to know that. All right, now here's a typical mitochondria. Again, the outer mitochondrial membrane. Here's the inner mitochondrial membrane. Electron transport occurs here. Electrons are passed along these complexes, 1, 2, 3, 4. Okay. And during these passing of electrons, it's like a snowball rolling down a hill at progressively stronger electron grabbers. That energy of the snowball rolling down the hill, the electron grabbing, is used coupled to pumping a proton into the intramembranous space. And now you build up a concentration gradient of protons that's very much like pressurized air. And then you release that gradient like taking out pressurized air by allowing a proton to pass through ATP synthase. It's also sometimes called complex 5. And when that proton comes through, it'll spin ATP synthase because it's a rotary motor. And in the spinning of it, a phosphate is added to adenosine diphosphate, di as in 2, to become adenosine triphosphate, tri as in 3. So adding the phosphate to it energizes this molecule, and it then travels around the cell to be used for energy. That's how life on Earth occurs. Over 90% of the ATP in our body is made from this process here in the mitochondria. Okay. This is life on Earth right here. It's worth knowing about. Okay, and so what is the boss of a cell? What controls a cell? What is like the light switch that turns a cell on? And it's this lady right here. Okay, this is mama. This is mama. Calcium, I gave each ion. I made all this stuff up because it's the best way to think of it. Calcium, in terms of ions, is like the mother. The mother is the boss of a family. Even if dad, he's bringing in the money, so what? She's the boss, all right? That's important to know because when calcium comes into the cell, Whatever that cell does, it must do it. Mama is not reasonable. Mama does not want a discussion. Mama just yells at everybody and tells them what to do. When I was a kid growing up, my mother would always just come in the room, tell us what to do, and if we didn't do it pretty fast, boom, she'd throw a shoe at us. Boom, another shoe. And you had to do what Mama said. Because if you knew if you went too far and you pissed off Mama too much, she'd call in Dada, or she would just pull out the belt and whip the crap out of you. And you know what? It was good my mother whipped me. I only got whipped about once for every 10 times I deserved it when I was a kid. And you know what? There were no behavior problems. There was never disrespect in my house. Anyways, be that as it may, the point of this slide was calcium is the boss. It's Mama. She's not reasonable. She comes in and she demands the cell do whatever that cell does. Okay, if it's a neuron, it releases its neurotransmitter. If it's a pancreatic beta cell, it releases insulin. If it's a vascular smooth muscle cell, it'll contract. Okay, so here is the example of calcium comes into the cell, neurotransmitter is released like glutamate in a neuron, whatever. All right, that's how normal cells work. But there's something else that's going on in a lot of cells that was hard for people to understand, including myself. There would be secondary releases of calcium. So here is a sarcoplasmic reticulum in a cardiac muscle cell, and there's analogous situations in other types of cells whereby, yeah, sure, you get some calcium coming in across the plasma membrane, but then you would get a secondary release of calcium from another location in the cell. And I learned also a word called microdomains, meaning localized areas of calcium concentration. So what was that all about? And now this is a little bit preliminary, but from the papers I read, what they think is happening is that the calcium is fluidizing the gel, the water's in a gel phase, and then when they want something to run faster, calcium comes in, hits the area, and it fluidizes the water, liquefies it, and then things can happen, like the cardiac muscle will contract, the skeletal muscle will contract. Whatever the cell does, that area will become active when its microdomain gets increased calcium. So this is a really cool thing because it enables a cell to compartmentalize its activity and just have calcium locally where it wants to be active. Okay, so I made another metaphor for this. So in this metaphor, here's Mama, okay, and she's just laughing her ass off while dear old Dad is getting picked on. She has her sister come over and the other sister. These are the two aunts, and there's Grandma, and she's messing with the old guy. And you see how the old guy, he's not a total fool. He's got his hand out back because he knows one of the ants about coming ready to smack him on the bottom. So the relevance is, what I'm trying to say is, calcium recruits more calcium, more females, more estrogen. And they're just picking on the poor old guy who's trying to get the work done and pay the bills. And so of course I'm joking a little here, but the point of the matter is secondary calcium from different locations activates different parts of the cell. And the calcium ladies are running the show and making whatever happen around the house that they want to have happen. And that's how women run a house anyways. Little passive social manipulative games and power plays and alliances and stuff. So anyways, this is secondary calcium release to control secondary processes in a cell. I'll show you one more example of that. Like this could be even in a neuron, okay? You can release IP3, an inositol trisphosphate, and that can cause release of calcium from the endoplasmic reticulum. Okay, it can even cause release from the endoplasmic reticulum for something called the ryanodine receptors. All of these things can cause little localized calcium release to activate different parts of the cell. And this idea of, well, nobody quite understood, why is it doing this? Why doesn't calcium just come in from the plasma membrane? Why is calcium being released from all these separate little locations? And what appears to be the understanding at this time, don't get me wrong, I'm not completely sure if this is all going to be proven out in the long term, but this is what seems to be happening from the papers I read, is that you're getting local fluidization of the gel to increase the activity in localized parts of the cell. Okay, in the future we'll understand it better, but that's what seems to be going on, and I think that's quite interesting. So anyways, that's the point of the paper today, and the biggest thing out of this whole paper was the idea that infrared light, which you only get from the sun and from incandescent bulbs. You don't get it from LED lights, you don't get it from fluorescent lights in no significant amount. You don't get it inside your house if you live in an apartment or a skyscraper or something, because you'll probably have low E glass, low energy glass, that blocks out the infrared light, so it can't get into your house, to save heating costs, so you can't have heat exiting your house. But anyways, I hope you found that interesting.